So this is going to be the last lecture on LDPC block codes. Tomorrow we'll start with the convolutional codes, convolutional version of these codes, which we now call spatially coupled codes. And I'll explain the reason for that tomorrow. So this lecture has a number of different topics that are more, not so much detail as we've had in some of the previous lectures, but more of an overview of just different aspects of LDPC block codes that we haven't spent any time on yet. And the first is encoding. So if we think back to block codes, if we start with an H matrix, the way to get a generator matrix for the code so we can encode is to first convert the parity check matrix to this form. It's called reduced row echelon form, but we have a identity matrix here, and then it's easy to convert this to a generator matrix like this, such that GH transpose is equal to 0. So that's when we do LDPC codes, we construct the code from the point of view of the H matrix. And it's usually not in this form. In fact, it's really never in this form. Okay. So we can use the so-called Gauss-Jordan elimination technique just to convert it to systematic form, and then we could get the generator matrix that way. Now, the problem with this is that G, if we do this, G won't be sparse. For one thing, it's difficult to do for big codes to start with, and G would not be sparse in general. So the encoding then would be complex. It would be order of n squared. Now, encoding is not as big an issue as decoding usually. It's the complexity of the decoder that we're most concerned with. But encoding complexity is also important. I mean, all the kind of standard coding techniques that you're familiar with have linear encoding complexity. So if we didn't do anything about this, this would have quadratic encoding complexity in the block length. So since H is sparse, it would be nice to encode somehow from the H matrix and not have to convert to a G matrix, which wouldn't be sparse in any case. So we can do that. There's a way of doing that, kind of. And we say here, almost linear encoding. So you want to, first of all, take the H matrix. Now, the notation here, remember that if we have only independent rows in the H matrix, we have n minus k rows in the H matrix. But in general, with these kind of low-density constructions, the random constructions, we may get additional rows we may have some redundant rows. So the number of rows in the H matrix in general is m. Okay, it can be more than the number of independent rows. Okay, so that's usually the kind of H matrix we would start with. Now we can put it in approximate lower triangular form, and we'll say that this is a lower triangular matrix. Would have a diagonal row of 1s here, and then everything above the diagonal would be 0, and we'd have non-zero terms only below the diagonal. That's a convenient form. Okay, it makes it easy to find inverses, for example, if a matrix is in this form. So we can take our H matrix and convert it to this form in the following way. We express the H matrix like this. We split the rows into two groups. Let me start differently here. We look at the kind of upper right corner of the matrix, which is what we're going to try to get in this lower triangular form, and we see how many rows of this matrix we can get in this form. Okay, we say here this is done offline. So this has to be done just by hand, if you want to think of it that way. Or you could write a program to do it. But you want to have a lower triangular form matrix over here with as many rows as possible. So the remaining rows G want to be a small number. Okay, now it just depends on the matrix you start with as to how well you can do this. And this is going to be a square matrix which will be size m minus g by m minus g, and then the remaining g rows will include down here. Now, the other part of the matrix here will have m minus g rows which have g columns. Otherwise, we'll take just g columns here, the g columns here, and call it B, and the g columns down here and call it D. Where again, we want g to be small, so we'd have a few columns here, if you want to think of it this way. And then the rest of the columns would be over here in A and C. Now there's a typo here, or a handwritten minor error. This actually wouldn't be k, because as I said, it would be k if m was exactly n minus k. Okay, because then we'd add up the number of columns, m minus g plus k. If m was exactly n minus k, we'd get n. But m could be bigger than n minus k. So what we really need here is m minus n. Okay, so we make sure we have n columns. Now again, that will be k if, or we need, excuse me, n minus m, not m minus n minus m, which will be k if this is an equality. Okay, so we typically have a large number of columns here, small number of columns here, large number here, large number of rows here, and a small number of rows here, if we can make this g small. Okay, let's just look at this little example. Now we don't have upper triangular form or lower triangular form in the upper right hand corner here. So we can always interchange rows without changing the code. Okay, and we can interchange columns without changing the code. Again, changing column positions, it doesn't change the weight structure of the code. All it does is change the order of the bits. So that's okay as long as you remember you've done it and you tell the decoder that you've done it. Okay. So if we swapped rows 2 and 3, just interchanged them here, again, that doesn't change the dual space of this matrix is the code. Just interchanging 2 rows doesn't change that. So interchanging these 2 rows gets the 1, 1, 1 up here, okay, and we get a 0, 0, 0 down here, okay. But then if we swap columns 6 and 10, we'd get, the rows have been interchanged, we'd get 0, 0, 1 here in column 10, and we'd get 0, 1, 0 over here in column 6, okay, and the same thing for the other bits. But if we make those 2 operations, we can get the top 3 rows here in this lower triangular form on the right-hand side of the matrix. Now we try to do this as best we can. It turns out with this matrix you can't get a 4 by 4 lower triangular matrix just using these kind of operations which don't change the code. So now we have it in this form. This is an equivalent H matrix. And the next thing we want to do, and this is again done offline, is we want to get rid of this matrix. We want to get a 0 there. Okay? So we want to do operations, again, just row operations on this matrix, on this H matrix, which will not change its row space. So we don't want to change the upper row at all. So we multiply this thing by an H tilde, which is of this form, which has a first row, which is an identity, m minus g by m minus g identity, and then 0. And what that's going to do as far as when we multiply it by h sub t, it's going to leave the first row unchanged, abt. The second row it's going to change. Okay, it's going to take minus e, and we can forget the minus signs because this is modulo 2 addition, so minus is plus. But if you were doing it in some other field, you'd have to use minus. So you multiply by e, times the inverse of t, the first row, and then the second row times the identity. Okay, what is that going to give us down here? Well, it's going to give us E t inverse times A plus C. Okay, and that's indicated here as C tilde. And then for these columns, it's going to give us E t inverse times B plus D. And that's indicated here, E t inverse B plus D. And that goes here, we call it D tilde. Okay. The important thing is what it does with this entry. It gives us T inverse times T as an identity, multiplied by E gives us E. We add it to E, and we get 0. So we can knock out E that way. Now again, all these operations are just linear operations. So they're not changing the row space, they're not changing the null space of H. So we're not changing the code. Okay. But we have, it's important, we'll see that we get a 0 in this lower right-hand corner. Now the other thing to observe with this is the first block of rows here, which is the big block, assuming we can make G small, it's unchanged from the original matrix. Okay, so it's still sparse. I mean, the original matrix was sparse, and we just interchanged some rows or columns, but that's not going to change the sparsity. So these rows are still all sparse, not very many ones. Okay, the second block of rows here could be dense because we did this. Okay, and that, in both of these cases, these multiplications could introduce additional ones. So the lower rows can be dense, but hopefully there's not too many of them because they're going to be involved in encoding. And if they're dense, that makes the encoding more complex. Again, to do this, we'd need to find T inverse and perform matrix multiplication to do these operations. So that's one of the reasons to have this T in lower diagonal, lower triangular form, because it makes it easier to find the inverse. Okay, so doing this example, it turns out that here was our original T in lower diagonal, lower triangular form. T inverse, it turns out, is just equal to T in this case. You can see that if you take this matrix and multiply it by this. This just preserves the first row. This adds the first two rows, which knocks out this one, but leaves this one. And this preserves the third row. So this times this is the identity matrix. So that makes this the inverse of this. So it's, again, if you have lower triangular form, it makes it easier to find this inverse, which is the reason we do this. Now, the other matrix that we wanted to do to multiply H by was this thing, okay? And if we carry out that operation, this is M in our case is 5 and G was 2, so we got a 3 by 3 identity matrix here. We got this 0 matrix here. We got a 2 by 2 identity down here. And this is E times T inverse. So to get this, we'd have to take our E from the previous version of the H matrix, which is going to be this 2 by 3, and multiply it by T inverse, which is this 3 by 3, and we get a 2 by 3. And that gets multiplied, that's just this 2 by 3. Okay, so I'm not going to go through the calculations here, but this ET inverse is the lower 2 by 3 matrix in this bigger matrix. And we get this, just as I said, go back to the previous version of the H matrix where we have a 2 by 3 E, multiply it by this, and we get this. Okay, if you check it, but I don't want to do it here because it's a lot of flipping back and forth among the slides. Okay, so then you get, if you multiply this then by the previous version of H, you're going to get this form. Remember, the top 3 rows are not changed because of this identity matrix. And this is designed to give us a zero matrix down here. And when we multiply E T inverse by A, okay, and add it to the lower part, we wind up getting this. And when we multiply E T inverse by B and add it to the lower part, we wind up getting this. Well, again, you don't have to worry about the minus sign. I would have rather we didn't put them in the slides because it's modulo 2. So it's just ET inverse. You're multiplying and doing all the operations modulo 2. So this is just this example of what these two matrices here are these two things. Okay, and again, rather than flip back and forth a whole bunch of times to show that that's right, I did check it, actually. It is right. It's easy to make mistakes. But you get this form of the H matrix. So now we have it in this form. This is still sparse, the upper part. We haven't changed the sparsity of the upper part. The lower part, well, this is pretty sparse because it's all zeros, but this in general is not going to be sparse. So we encode in the following way. We can do a systematic encoding, and the thing that we're doing here, which is a little different, we're encoding from the H matrix, from the parity check matrix, or a modified version of the parity check matrix that we started with. But converting a parity check matrix that we start with to something like this is not difficult. These operations that we've talked about and we've said can be done offline, they're not difficult to do. Although the bigger the code is, the harder they are to do. But given that we have the matrix in this form, we can actually do a systematic encoding. So the code word will come out in this form. Now we're not even looking at the G matrix here. Okay, we're encoding directly from the H matrix. So how do we do it? Well, we know that VH transpose must be equal to 0. For any valid code word V, or the other way of writing it is HV transpose must be equal to 0. And with this H, that implies that if we write V as an information part and then a parity part and then another parity part, again, I've said that this K should be N minus M in general, which could be bigger than K. No, N minus M, it could be smaller than K, right. It could be smaller than K. K could be bigger than N minus M. So what happens in that case? Well, it's just not a systematic encoding. Well, it would not be a systematic encoding then, because we have K information bits, but this part could be less than K bits. So it would be partially systematic. Otherwise, if we had one redundant row in the H matrix, this systematic part would be one bit less than it. It'd be like having a G matrix which had all your columns of an identity matrix except there were one or two missing. Okay, but it's still a valid encoding, whether it's systematic or not. Okay, so let's think of that, just to not bother with that detail, let's think of this N minus M as being equal to K. We got a systematic part, a first parity part, and a second parity part. And if we multiply the transpose of this by H, we're going to get A times U transpose plus B times P1 transpose. By the way, this is hopefully a small, short vector, because it's just got G bits, and G was what we're trying to make small. And then we'd have T times the second parity part. And then from the second set of rows, the second row here multiplied by V transpose, we're going to get C tilde times U transpose plus D tilde times P1 transpose plus 0 times P2 transpose. Okay? So these equations must be satisfied by any code word. Now, how do we do the encoding? Well, that's the reason we got the 0 in here, that we converted this to have a 0, is we can now use this equation to solve for P1. Okay, so we just take d tilde inverse. 0 drops out. We multiply this by d tilde inverse, and we can solve for P1. So we get P1 is equal to d tilde inverse times c tilde times u. Okay, so that would give us the P1 transpose. And the complexity of that, these are not sparse, so the complexity would be quadratic. But if G is small, and we tried to make it as small as we can, then this isn't too bad. Okay. Now the rest of it, P2, we can get this way then. Once we've got P1, we can solve P2 from this equation. And the way we've written it here, we've said, well, we multiply by T inverse, which would give us a T inverse here, and then we'd have AU plus BP1. Now T inverse, you may wonder, well, that's that lower triangular. Is that guaranteed to be sparse or not? T is sparse, but does that make T inverse sparse? Okay. I mean, not necessarily. I mean, these lower triangular matrices, they have they're semi-sparse to begin with because they've got a whole half of zeros. But you don't actually have to use this directly anyway. The way you do it is slightly different, where you don't have to use any matrix that might not be sparse. So let's just do the example here and see how it works. So we've got P1. These are the equations. This turns out to be the inverse of d tilde. This is C. And if we had an information sequence U here of this, we just do this operation and we get 1, 0 for P1. Again, this is going to be order of G squared complexity because we can't guarantee that these things are sparse. But G is small, so that's not going to be very complex. P2, on the other hand, we could do it like we indicated here. It's essentially the same thing. But we can go back to the form here. And the P, when we multiply this by V transpose, the P2 is affecting these three columns. So what we see here is the first bit in the vector P2, it must equal the sum of these 4 bits from the U part, from the information part. So U0, U1, U3, and U4. So we can take, that forms the first bit in P2, U0, U1, U3, and U4. And we read those right off of this. Okay, now for the second bit in P2, that's going to depend on the first bit in P2, which we just calculated, and the first bit in P1, which we had previously calculated, and this information bit. Okay, so again, this is another reason for the lower triangular, is you can calculate these bits in the P2 vector kind of one after the other and use the previous calculations, if necessary, to calculate the remaining bits. So that's this equation. We have the previous bit that we just calculated, P2. We have the first bit in P1, and we have the U3 bit. And then the last bit in P2 we get from the second bit in P1, which we previously calculated, and these 3 information bits. So that's shown here, U1, U2, and U4. And the second encoded bit in P1. And we add those up, and that gives us the third encoded bit in P2. We didn't invoke that T inverse here at all. We just encoded, because of this lower triangular form, we encoded these 3 P2 bits in sequence using these 3 rows, and these are all sparse matrices. So that's a sparse operation. So we wind up then with an encoded word, which is the information part, the P1 part, and the P2 part. And it's in systematic form, at least if m is equal to n minus k. And in decoding, we would have to remember that we have, we encoded this way, we change the order of column 6 and 10. So the decoder would have to remember that, or would have to know that in order to decode the code word in this form. But we would just, that would be known ahead of time. Is there any question on this? So that the idea is just that the encoding in general is more complex for low-density parity check codes than it would be for standard linear block codes. It's order n squared rather than order n. But you can change the form of the H matrix in such a way that you can encode directly from the H matrix, and depending on how large you can make this lower triangular matrix, you can make the encoding complexity almost order n. So it's not a big deal otherwise. The fact that you would in general have encoding complexity of order n squared, if that bothers you, you can do this and you can get it essentially of order n. So that's kind of the message of this first part here. Okay, so the next thing, we want to talk now about some structured parity check matrices. We've been talking a lot about random constructions. And random constructions are nice because you can analyze distance properties, you can use density evolution to analyze thresholds, etc. But structure is nice for implementation. So quasi-cyclic codes in particular, a quasi-cyclic block code is a code which has the property that any cyclic shift of a code word by some number of places results in another code word. So a cyclic code is just if C is equal to 1, we have a cyclic code. Otherwise, any code word you have, if you just cycle it by one position, it's still must be another code word. These are a lot of common codes are cyclic codes. BCH codes are cyclic codes. Reed-Solomon codes are cyclic codes. And a lot of the early Hamming codes are cyclic codes. Golay code is a cyclic code. A lot of the early work in algebraic coding theory focused on cyclic codes because they had an easy shift register based method of encoding. So if we can, and it extends also to quasi-cyclic, except with quasi-cyclic you would need to use multiple shift registers. With cyclic codes you can do it with one. But it's still an easy way of encoding. So if we can build that kind of structure into an LDPC code, it makes encoding easy. We don't have to worry about what we just did. But it also helps in decoding because there's a cyclic structure in the decoder, and it allows us to use some parallel implementations that can result in higher speeds. And as we'll see later, this is almost always used in, these kind of codes are almost always used in standards. So this is a little example of a quasi-cyclic code with C equal 3, but I won't spend a lot of time on it. Here I just want to give a flavor for what you do with these things. The so-called row circulant quasi-cyclic code has a parity check matrix like this, where the columns are divided into L groups, and each group is an M by M circulant matrix. So a circulant matrix is just a matrix where each row of the matrix is a cyclic shift of the previous row. So if, for example, if you had a circulant matrix was a generator matrix of a linear block code, it would be a cyclic code. If you have a generator matrix, which is a set of circulant matrices, you're going to have a quasi-cyclic code. Here we're talking about making because we're talking about low-density parity check matrices codes, we're talking about making the H matrix circulant matrices. So here we'd have a total of L M by M circulant matrices, so we have LM rows and L columns. Or excuse me, M columns. Said that wrong. LM columns and M rows. So if L is large, these are going to be high rate codes. I mean, this is a construction for high rate codes. If L is 2, we get rate 1/2. If L is 3, we get rate 2/3, etc. And M can be big. Now, if one of the matrices is invertible, all we require is one of the matrices being invertible, then we can multiply its inverse by itself to get the identity matrix, and then we can multiply through all the matrices, the circulants in the parity check matrix, and we'd get one of them will turn out to be an identity, and then the others will turn out to be something else, okay? But that allows us to convert this to systematic form, okay? And then convert the H matrix to systematic form, and then we can immediately get a G matrix for that code. So it makes encoding very straightforward. We just have to pick one of the circulants as being an invertible matrix. So this is a typo. This would result not in an ML-1 ML code, it's ML ML-1. The first number should be the block length, and that's ML. And the second number should be the number of information bits, and that's ML-1. Again, this is the kind of the nominal rate. There could be redundant rows. No, there won't be in this case, because we convert it to systematic form. Same type of argument as we just talked about with the other problem. So here we have linear time encoding. We need L-1 shift registers of length n. But this becomes very easy for encoding. And it has implementation advantages for decoding also. So we can give a little example here. This would be a rate 1/2 circulant code, just 2 submatrices. Notice the circulant structure. Otherwise, each row here is just a shift to the right, and then we shift around here of the row above it. And this has the same structure. Everything is shifted to the right with a cycle around for the last bit. Now, this isn't something that we've covered, but when you're working with circulant matrices, there's an easy, you can represent a circulant matrix with a polynomial, and it makes it just easier to see what's going on. You take only the first row. The only thing you have to know about a circulant matrix is its first row, because then all the other rows are determined. And if you just let that be represented by a polynomial, that's a compact description of a circulant matrix. Otherwise, 1 plus x, indicating the first row here, is a complete description of this matrix. And 1 plus x squared plus x to the 4th is a complete description of this matrix. So it's a compact way of representing, and you see this often if you've ever studied cyclic codes. The generator polynomials and everything, or the generators are always represented by polynomials like this, okay? Because that represents any circulant matrix. So we could write the matrix in polynomial form, the parity check matrix, in this way if we want. Oh, somehow that x to the 5th plus 1 got in one animation too soon. Now, it turns out A2 is invertible, okay? So we can convert this to systematic by multiplying this by its inverse, and then multiplying the inverse by this, And if we do that, now the computations here are indicated in polynomial form. I'm not going to go through them, but this is the inverse matrix of this. And what that says is if we have a circulant matrix which has of size 5 by 5, which has the 3 ones over on the right. So it would be, the first row would be 0, 0, 1, 1, 1. If we multiply that by this matrix, we're going to get the identity matrix. So you can work that out. I mean, if you're not familiar with the polynomial representation, you can just find the inverse of this matrix. Okay. And then you have to multiply that by this. That's what this operation is, multiplying the inverse of A2 by A1. And of course, this has to be transposed, because when we flip from the H matrix to the G matrix, we got to transpose the rows and columns. So we wind up with this being 1 plus x squared, which means it would be a 1, 0, 1, 0, 0 in the first row, but the transpose of that is 1 plus x cubed. So we'd get 1, 0, 0, 1, 0 in the first row. And then everything else is just the shift of that. So we can do that again. I'm not going to go through this. If you're not familiar with it, we didn't cover it in the block code part. But it's a convenient way of dealing with these kind of circulant matrices. But the point here is that this again is a row circulant quasi-cyclic code. We can find the inverse of this matrix, get an identity matrix here by multiplying by that. We get a parity matrix then here by multiplying by the same thing. And then we convert it to the form of a generator matrix, and we have a systematic encoder. It makes encoding easy. It's not necessarily sparse. This won't necessarily turn out to be sparse. Even if these circulants are sparse, the inverses are not necessarily sparse, but you have a systematic encoding. So it's still an easy encoding. Okay, again, these are a lot of little topics here that are highlighted in our notes here, but not so much detail. An extension of this is a block circulant quasi-cyclic code, where you just, instead of having one row, you have j rows. So these are more, can allow more parity checks, and you can have lower rates with block circulant codes, because the row circulant codes are, by necessity, they're rate 1/2 and higher. So these are more flexible than row circulant quasi-cyclic codes, and a lot of there's been a lot of work on these codes in recent years, and most of the codes in standards actually have this form, okay, because of the implementation advantages. So the LDPC codes have been designed in a number of different ways. I mean, there's the geometric algebraic structure, which we had in our book, guarantees no force cycles and a large minimum distance. Progressive edge growth is kind of a computer search algorithm which can eliminate graphs with short cycles, so give us larger girths. And a protograph construction, we're going to talk about that now, is a way of constructing larger graphs from small graphs with a certain structure which guarantees us some good properties. And there's lots of others. So far, kind of what we've and this is actually not the end of the lecture. There's a little bit more. We've got a summary here a little prematurely, but LDPC codes, so they're designed on sparse, random-like bipartite graphs. You have efficient order n, but suboptimal decoding using belief propagation, iterative decoding. The encoding can be order g squared, where g is much, much less than n. Okay, or it can be even linear if we use quasi-cyclics. JK regular codes in general have good distance and graph properties, like trapping sets, stopping sets, and things, but poor decoding thresholds. So the waterfall performance is not as good in general, but they typically don't have error floors. Irregular codes can be designed with good thresholds, but they're going to have poor distance and graph properties, which means usually bad error floors. And structured codes can sometimes bridge the gap between these two types of codes. So here's one type of structured code which it's similar to the block circulant, except these are just permutation matrices, which are not, so there's a permutation matrix as just a single one in each row and a single one in each column. So with that property, if we have j rows here, that means we've got column weight j, and if we have k columns here, it means we must have row weight k. So if we fill up a matrix like this with these are always square matrices, m by m permutation matrices, we get a jk regular ensemble. This is something like the Gallagher ensemble. It's just a little bit different. It is similar to the Gallagher ensemble, but it has a structure that makes it easier in some ways to analyze. So we actually get, from this ensemble of JK regular codes, we get exactly the same distance growth rates as we got for the Gallagher ensemble for a given j and k. And an example, we would say, okay, for j equal 3 and k equals 6, if we substitute in, if we use 4 by 4 permutation matrices, we'd get this code of length 24, and it would actually have 12 rows, so it's a rate 1/2 code. Assuming there are no redundant rows again, because we could have redundant rows because these permutations are chosen randomly. If we wanted to construct irregular codes using this method, we could just take some of these matrices and replace them by zeros. Okay, and in this case, we would have then, in terms of the row weight, instead of all being 6, we'd have these 10 rows would have weight 5, would have degree 5, and these 5 rows would have degree 3, because we've removed 3 of the permutation matrices. We've only got 3 left. So we'd have a check degree distribution of 5 rows of degree 3 and 10 rows of degree 5. And then our column weight distribution could be, we have, we're going to have a set of four variable nodes of degree 3, and then we're going to have the other 20 are going to have degree 2, because we removed one matrix from each, okay, to give us degree 2. So there's a compact representation of structured codes like this using the concept of a protograph. And if we have an H matrix of the type we just described, which is of B sub C by B sub V dimensions with m by m permutation matrices or all 0 matrices substituted in, or as elements in this matrix, we can actually, there's a simple way of representing an ensemble like this, and I call it an ensemble because we can pick all different possible ways of picking permutation matrices will work here. So this what we call base matrix of size B sub C by B sub V can be used as a representation of this bigger matrix. And this base matrix has a graph like this. It's got 6 columns and 3 rows, so it's got 6 variable nodes and 3 check nodes. So we can actually view this kind of structured code from the point of view of this protograph representation using a small base matrix or a small graph. And that makes it easier to look at the properties of codes of this type, because we can do the analysis on the small graph and it applies to any of the codes in the ensemble that we would get by substituting permutation matrices in for these ones. So this protograph construction in general, I mean, that's one way of looking at it. We look at starting at a structured H matrix and then going down to the protograph representation. Another way is just thinking of it as starting with a small graph. Here we have 3 check nodes and 4 variable nodes. And then you do a copy and permute operation. Copy just means you replicate the thing, say 3 times in this case. This is the m by m size of the permutation matrix that we wind up substituting into these base matrices. Now, then we permute, which means, say we look at the edge from variable node 0 to check node A in each of these copies. Well, we could flip those around now if we want. We could put this one over here, and leave this one where it is. Okay, so we make a bunch of copies. We think of it this way. We can think of it this way. Making a bunch of copies of a small graph and then permuting the connections, but always keeping the zeros all go to an A, but they don't necessarily go to the A in the same copy. So there's a permutation that goes on. That's equivalent to replacing those ones in that base matrix with a permutation matrix. This is just a way of looking at it graphically. So we just do this. We want to maintain the 0 nodes always go to 1A and 1C check node. It's just that they don't necessarily have to be in the same group. And that's the permutation operation. The code rate, just like any of these codes, is the number of variable nodes minus the number of check nodes divided by the number of variable nodes. And again, it could be more than that if you've got redundant rows. And the code length is this is sometimes called a graph lifting factor. It's the size of the permutation matrix if you're thinking in terms of the H matrix. And it's that times the number of variable nodes in the original base matrix or protograph. This idea originally came out of a PhD thesis at Caltech. And again, it gives us a nice visualization for constructing large ensembles of LDPC codes with certain guaranteed properties. So every member of a protograph-based ensemble is going to preserve the structure of the base protograph. That's because I said that the 0 variable nodes that go to A and C, say in that example, every 0 variable node in the bigger graph, one of the edges has to go to an A node and the other one has to go to a C node. And as long as we keep that structure, then all the codes in the ensemble, which are all possible permutations, will maintain the same properties as the protograph. So sometimes we draw these graphs like this now, the lifted graph, where we just indicate on each edge a permutation. An m by m matrix which has a single one in each row and a single one in each column. And the ensemble basically is a way of, these are different permutations in general, would just be all possible ways of choosing these permutation matrices. Would give you an ensemble of codes with this structure. Now, density evolution, I think I'm not going to dwell on this because it's late in the day and the details aren't so important. They can be performed on the protograph. It simplifies the calculation of the threshold because you're operating on a small graph. And also you can do an ensemble average weighted enumerator which allows you to calculate the minimum distance growth rates of these ensembles, assuming they're asymptotically good, using the same kind of analysis that we use, say, that Gallagher used, or that we use for turbo codes, for example, to get the weight distribution. And so it's not so hard to find the weight distribution of all the code words in a small graph like this. And then you can apply averaging techniques to get the average minimum distance of all the codes in a big ensemble. So I think I'm going to, this is just illustrating that you can do density evolution on a small graph like this. It can be described analytically for a binary erasure channel. If you're looking carefully at this, you may be confused because the notation here is not the same note. It's the special notation for the protograph version of density evolution, and it's not exactly the same as what we used previously. So if you want to understand this, you'd have to go to one of the original papers. So that's just to say you can do the density evolution on the protograph, and it's simpler than doing it on a big graph. It's essentially the same procedure. The distance analysis is, and again, there's details here that I'm skipping. We wind up trying to, this is just a way of viewing the result. You use something called the uniform interleaver analysis, which is basically you're just averaging the minimum distance over all possible permutations that you could substitute into this graph. And you wind up in the limit as n, this is going to be a complicated expression in general, but if you take the limit as n goes to infinity, there are simplifications that occur. And you can get this function as the limit as n goes to infinity of the average weight enumerator. So this is just the average number of code words of weight d in a particular ensemble. And you take the log of that and divide by n, and that's the definition of this function. And I don't expect you to understand this, but I just want to make one point with regard to it. The function typically looks like this for ensembles that are asymptotically good. Otherwise, if the protograph happens to correspond to an asymptotically good ensemble, you'll get a spectral shape function, it's called, that looks like this. And again, this is essentially the way Gallagher got his results. On the x-axis here, we plot the delta, the distance growth rate. And the y-axis is just is the value of the spectral shape function. What it implies, if r of delta is negative, which it is here, okay, up to some point, delta min, we'll call this value of delta, where it's equal to 0. And then it's positive after that. Then this delta min is the asymptotic minimum distance growth rate of the ensemble, which says that most codes in the ensemble will have a minimum distance at least delta min times n. The same kind of expression we looked at the other day with the Gallagher ensemble. And if you look carefully at this, you'll see that the crossover point here is 0.023. So this is the spectral shape function for the 3/6 regular ensemble, which had we said had a distance growth rate of 0.023. What this essentially says is that if the spectral shape function is negative, it means as n is getting large, as the block length gets large, the probability that this spectral shape function, there's a log in here, is like a coefficient in an exponent. And if it's negative, the exponent is negative, which means the probability that the minimum distance, that there are codes in the ensemble with minimum distance equal to this value is going to 0, because it's negative, exponentially to 0 as n gets large. So it's saying that as n gets large, the probability that any code in this ensemble has a minimum distance in this range is 0. When you get above here, you're saying that the probability that you find codes with minimum distance equal to this is getting large. So this point where it crosses 0 is the value of the minimum distance growth rate that you expect most codes in the ensemble to have, okay? And as n gets larger, that becomes a more accurate estimate of the distance growth rate. So we can say for large values of n, we can roughly multiply by 0.023 the block length, and that's going to be a very good estimate of the minimum distance of any code we would pick out of this ensemble randomly. So with high probability, we can say most codes in the ensemble have a minimum distance that grows linearly with that. Again, this is just, I don't expect you to understand where, unless you've seen it before, okay, where this comes from. But it's just, as I've indicated, the important thing, I guess, is to say that with a protograph, where you have a small graph like this, it's easy to calculate a weighted enumerator like this. And then you can go through this uniform interleaver analysis, which is kind of standard for analyzing distance properties of large ensembles. And you can get the minimum distance growth rate of the ensemble. If the spectral shape function never crosses 0, if it starts here and goes straight up, then the ensemble is not asymptotically good. So some of the irregular, if you start with an irregular protograph, which has degree 2 variable nodes, you're likely to get a spectral shape function that takes right off and goes up. So it can't guarantee that the distance grows linearly with block length. Again, it's a lot of, and I got one more here. You know, if you have patience, I'll hold you over for another 5 minutes. A lot of little kind of bullet items of different kinds of LDPC block codes that relating more to what kind of code we see in practice. So the question is, what makes a good protograph? Okay, well, a good protograph would be one with a good iterative, the ensemble based on that protograph would have good minimum distance growth rates and good thresholds. Okay, that's what we're looking for. And this is by far not the only class of protographs that have been looked at. There's all kinds of them. But these are very interesting ones, and they perform quite well. The repeat accumulate class of protographs, basically all designed by people at JPL in the NASA's JPL location in Pasadena. So this is a funny kind of example. This is a repeat accumulate code. I don't want to do any details here. The repeat accumulate code, when we talk about low density parity check codes, we're talking about defining something based on the H matrix. Defining the code based on the H matrix. Here, this is the repeat accumulate encoder. So the repeat accumulate code is actually defined in terms of the encoder. Okay, this is a repeat code. We have a bit coming in here. It's repeated 3 times. We take the 3 bits. We put them through an interleaver. So, and this interleaver it's not just a 3 by 3. It could interleave a large sequence of bits. And then it goes into a little rate 1 convolutional encoder. We had this as an example in class the other day, 1 over 1 plus d, which is called the accumulator. And I think I mentioned at the time that what it does, it kind of accumulates all the inputs. And the output is always the parity of all the past inputs. If all the past inputs have odd parity, the output is a 1. If they all have even parity, the output is a 0. So that's what's nice about it, it's a very simple encoder. Okay, so this is not so much, these codes were not invented so much with the concept of low-density parity check codes. They were invented more from the concept of simple encoding. But you can, if you look at the, I mean, this is an encoder. You could make an encoding matrix for it, a G matrix, and then you could look at a corresponding H matrix and form a graph. And if you do that, you get a graph that looks like this. And it's difficult to try to relate this graph directly to this. It's not like you have when you have an H matrix and you immediately form the Tanner graph. But this graph, variable nodes and check nodes, code words which satisfy these relationships are the same code words generated by this encoder. And given this graph representation, and this is a small graph because this is so simple, what makes the code bigger is you would have a big interleaver in here. But you can analyze the performance based on the small graph, which would basically be corresponding to the case where you don't have an interleaver here. Okay, and you find out that the threshold is 0.52 dB. This is rate 1/3, by the way, because you got an input coming in, and you wind up sending 3 bits over the channel. So the capacity for rate 1/3 is, I think it's minus 0.4 dB or something like that. So this is about within a dB of capacity, but not that close. But for very simple encoding. But these are not asymptotically good. I mean, this is an irregular graph, okay, and there's a so-called punctured node here. It's not, if you looked at this, there's 4 variable nodes and 3 check nodes, so it would be rate 1/4. But if you puncture one of the variable nodes, then one of the outputs goes away. You've got rate 1/3. So puncturing just means you delete it. You could generate that bit and then not transmit it. So that makes it rate 1/3. But it's not a regular graph in the sense that degree here is not the same as these degrees. And we've got 3 degree 2 variable nodes. So it's not surprising that the punctured node is still involved in the decoding and everything like that. It's just that you ignore it when you come to, I mean, it's still part of the connections between the various checks and variable nodes, but you don't actually transmit it and you don't decode it. But if you do the analysis, the distance analysis on this, they're not asymptotically good. So these guys kind of started with this, these repeat accumulate codes, which are basically a form of turbo codes. It's a serially concatenated turbo code. Okay, most turbo codes are parallel concatenation. This is serial concatenation. This is an outer code, and this is an inner code. Okay, and you've got an interleaver in between. So they started with this from the point of view of a turbo-like code, very simple encoding, and they were thinking of, okay, what does this look like if we thought of it as an LDPC code, and could we analyze the threshold and the distance growth properties, etc. Now, you could analyze the distance growth properties using the uniform interleaver analysis, but it wasn't easy at least at that time, it wasn't. The idea of developing thresholds for encoding structures like this hadn't been done. So they kind of converted it to the parity check domain, were able to analyze the thresholds, saw that they weren't asymptotically good, which they already knew that. Okay. Then they started to think, well, how could we take a protograph like this and maybe change it so it was asymptotically good, and we'd still have good thresholds? And they came up with something called accumulate, repeat, jagged accumulate, ARJA protographs. Okay, and they're similar, but notice they're a little bit bigger. They still have a punctured node. They have 5 variable nodes, including the punctured node, 3 check nodes. So the base matrix corresponding to this protograph is a 3 by 5. Now notice here, this is all in the graph domain. There's no encoder anymore. I'll get back to that in a second. But this is the base matrix corresponding to this graph. By the way, here's a degree 1 node that we were talking about a little bit this morning. This node is punctured. We basically mean that this corresponding bit is actually not transmitted. It's just these other 4 bits are transmitted. So we would have here in general, this would be a rate 2/5 code. Whoops. Because it's got 5 code bits and 3 check bits. Okay, but we don't transmit one of the check bits, so that would make it rate 2/4. So it is a rate 1/2 ensemble. When we look at this base matrix like this is what you were saying earlier. These integer values greater than 1 in the base matrix correspond to repeated edges in a protograph. Now this seems strange. You'd be connecting a variable node and a check node with 2 edges, or in this case 3 edges. Why would we ever do that? Well, we wouldn't do it if this was our code. But our code is going to be the lifted version of this. And when we take each of these and replace it by a permutation matrix, the chances that these nodes are going to be connected together essentially go to 0 when the permutation matrices get large. In fact, we should make sure in choosing the permutation matrices that they don't connect back to the same node. So you would not want to operate, you would not want to use a code with a graph like this. But the codes we use are the lifted version of this graph. So each of these nodes is repeated m times, and the permutations are spread all over. What that means in terms of the big H matrix is whenever you have a double edge like this, instead of having 1 permutation matrix, you have the sum of 2 permutation matrices. So instead of this little submatrix corresponds to a double edge, as does this one. Okay? Because it's 2 different permutation matrices added up. So the row weights here are 2 and the column weights are 2. And if we have a 3 here corresponding to a triple edge, we have the sum of 3 permutation matrices. And you know, with 3 by 3, there's only 3 of them. So they have to be different. You don't want to pick them the same. So that's one little restriction that you have to be careful of in lifting these graphs, is that if you're going to if you have non-zero entries or entries bigger than 1 in the base matrix, you don't want to pick, you're going to add multiple 2 or 3, say, permutations to make that entry in the big H matrix. You don't want to choose them to be the same.
What's the intuition behind doing this repeated entry?
Stronger codes.
How? Like
Well, you wind up with bigger degrees. So remember,
irregular kind of thing?
well, they are irregular because you want good thresholds and you want good distance. So these things, the repeat accumulate had good thresholds, but it didn't have good distance. So they were fiddling around with it, trying to figure out a way to strengthen the code and not screw up the threshold. Okay, strengthen the distance properties and not mess up the threshold. So they would want to increase the degrees of the variable nodes, same way we said whenever it was this morning or something. If you want to, with the irregular design, you want to get higher degree thresholds, higher degree variable nodes, strengthen the protection of those nodes. So they were, I think that was their thinking. is build stronger graphs by making the protograph a little denser. Now, since you're starting with a very small graph, the only way you can really make it denser is using these multiple edges. But again, when you expand it, that all goes away. So what did they, and then they had another, they could actually, that was a rate 1/2 design, as I said. If they just take that same design and add 2e additional variable nodes of degree 4. Again, these are fairly high degrees, 4. So they're, it would strengthen the code. And depending on what e is, if e is 0, you get rate 1/2. You get higher rates by adding more of these variable nodes. You got a lot more variables, the same number of checks. So they got a whole sequence of very nice codes. They got rates, say, from 1/2 up to 6/7. You can keep going. I just showed these in the table. Thresholds are, if you look, compared to capacity, they're kind of about 4/10 of a dB away from capacity, which is pretty good. Okay. And they have linear distance growth. Otherwise, the strengthening of the graph with higher degree variable nodes got away from made the codes asymptotically good, even though they're still irregular. The fact that they're still irregular gives them the good thresholds, but they have enough strength in the graph with the variable node degrees to give them linear minimum distance growth. They're asymptotically good, unlike the repeat accumulate codes that they started with. Now, the distance growth rates aren't as good as the regular codes. The rate 1/2 regular, 3/6 regular has a growth rate of 0.023. And if we go to 4/8, I don't know what would be comparable in complexity. Here, they're using a lot of degree 4s here. So I would say maybe 4/8 regulars would be more comparable in complexity. And there, the distance growth rate of the regulars is about 0.04 or something like that. Quite a bit more than this. But their thresholds are much worse. These are within 4/10 of a dB of capacity. The 4/8 regular threshold is more than a dB away from capacity. So they have here irregular designs that still have linear distance growth and good thresholds. They can't get optimum thresholds. The codes are too strong to get all the way to capacity, but so they're kind of an in-between thing. Now, one caveat, I'm almost done. This is almost an hour and a half. Okay. I don't think tomorrow well, I shouldn't say anything. Most of the lectures have been on time, and David warned me this one would take a long time. So now I forgot what point I was going to make. So I was talking about this trade-off between the thresholds and the distance growth rates. Okay, let's go on. Maybe it'll occur to me. So again, it's kind of an in-between thing. It's a little bit ad hoc. I mean, I think they did a lot of playing around with these. Oh, I know the other thing I want to mention. They did a lot of playing around with these graphs to get them just get the right trade-off between threshold and growth rate. The other thing I wanted to mention, which I always have, I've talked to these guys about it. Here we had a nice simple encoder. So it, that's really nice because usually you have to worry about encoding with low density parity check codes. But once they took this viewpoint in the H matrix domain with protographs and then started to modify them, I mean, they still call them accumulate, repeat, jagged, accumulate. The terminology of accumulate is still there. But what they don't tell you is you can't encode them this way anymore. It's very hard to find them to admit that in their papers because they don't admit it. And when you ask them about it, they say, well, they're just LDPC codes. You can encode them like any other LDPC code, okay? But somehow, I mean, a lot of people, including myself, and when I first saw this, thought that these maintained this easy encoding structure. Not true, okay? But still, they're a very nice class of codes. One quick thing on quasi-cyclics, I said they have one more quick thing on quasi-cyclics. They can be encoded with low complexity, and they also have efficient decoder implementations. This is just to show you can do quasi-cyclics with the protograph construction too. So we have a base matrix. For quasi-cyclic codes, the permutation matrices are circulant, which means they're shifted identity matrices. And this is just an example with size 7 permutations, a 2x3 base matrix, so we'd get a code of length 21. And these don't, I mean, if you have integers greater than 1 in your base matrix, you would add together 2 shifted identity matrices. So you'd have circulants of weight 2 or 3 if you wanted to make the codes more powerful with larger degrees. Important to realize, though, when you, and I think some people still don't understand this. I mean, you can work with, you can have a base matrix, and you can do your ensemble analysis on it, and it can have a very good threshold and very good distance growth properties. Okay. Then when you go to construct a code, if you pick your circulants, if you require them, you pick your permutation matrices, if you require them to be circulants, in order to simplify the implementation, all that analysis goes out the window. Okay, because the analysis is true only for randomly chosen permutations. When you put a restriction on how you choose the permutations, you can no longer rely on that analysis. And I think there are people that still don't understand that when you go to quasi-cyclics, you do pay, in general, you're going to pay you may be lucky and you may pick a good one, but you can't be guaranteed to pick a good one like you can if you choose randomly with high probability, okay? In fact, most of these, they will not have linear distance growth. There's too much structure. They may have good minimum distance for certain lengths, but they're not going to be able to minimum distance grow asymptotically with n. There's too much structure. So there are advantages, but there are disadvantages too. It's a suboptimal class of codes, but with some very nice properties with regard to implementation. And certainly if you're going to construct quasi-cyclics, it would make sense to start with a protograph with good asymptotic properties, okay? But it's just when you specify circulant permutations, you can't guarantee that you're going to realize those properties. I could tell you who still doesn't understand that, but I won't tell you. So this is the last slide. I'm sorry to go so long today. Turbo codes, this is your standard turbo code with a long pseudo-random interleaver, okay? 2 short constraint length convolutional codes, usually the same encoder, decoded using BCGR, iterative BCGR decoding. And again, you need BCGR because once you start the iterations, the probabilities of a bit being a 0 or 1 are no longer equally likely, because the iterations give you information about the reliability as you proceed. So the Viterbi algorithm is not optimum. It's only optimum if the input bits are equally likely. And in general, that's not true when you're doing iterative turbo decoding, so you need to use the BCGR. And our low-density parity check, these appeared in a lot of standards, and our low-density parity check codes are also getting into a lot of standards, defined differently using sparse codes on graphs, or sparse graphs, defined using sparse graphs. You've got a good idea about doing this kind of mixture, yeah. You mean one with real good threshold and another one with real good distance properties or something like this. Yeah. Well, I mean, look, I don't think that's really much different than try to find a protograph with good properties, both. What we'll talk about tomorrow is with the spatially coupled codes, you do get both. So the spatially coupled codes, you can start with a 3/6 regular structure, and you make a slight modification of it, and instead of getting these thresholds at 1.1 dB, you get a threshold at 0.3 dB or something like that. So you get, and the distance properties are essentially the same. So the spatially coupled codes are one way of trying to get good thresholds and good distance, as are these repeat accumulate type codes.